Today's talk is by Ming Li, and he's a faculty member at Horn Point. Ming's title is Fighting Surging Seas in a Changing Climate, Defending Coastlines at All Costs for a Strategic Retreat to Higher Ground. Ming received his PhD in Oxford in geophysical fluid dynamics. He worked at Victoria University and the Institute of Ocean Sciences in Canada before coming to Horn Point. Ming really has broad interest in coastal science. He's worked on estuary and coastal dynamics, numerical ocean modeling, regional impacts of climate change, sea level rise, and coastal flooding. And he also has an active program in coupled biochemical and geophysical models that look at causes of harmful algal blooms, hypoxia, and ocean acidification. So it's noteworthy also of today is Ming is the leader of a new NSF research coordination network that some of the participants are a member of. And that's advancing interdisciplinary research to build resilient communities and infrastructures in our nation's estuaries and bays. So they're having a webinar series as well. So Ming may let you know how to tune into that. So without further ado, I'll turn it over to Ming. And thank you all for attending.
Thank you, Mike, for the introduction. Thank you, everybody, for tuning in. In this talk, I will discuss how different coastline management affect an estuary response to sea level rise and storm surge in a warming climate. I will use Chesapeake Bay as an example of estuary and the same enclosed bays. Let's see whether they will turn the page. Yeah, okay. In October 2018, the emergency manager at the city of Virginia Beach declared, "We're at war. Sea level rise is public enemy #1. He was actually not the first one to declare war against the surging seas. About 1,000 years earlier, King Chen of Wuxi Kingdom in China led 500 of his best soldiers to the bank of Qintang River in in the city of Hangzhou, just south of Shanghai. They shot 3,000 arrows into the tidal boat shown here, or right here, in order to kill the evil river spirit. Interestingly, they also built dikes and seawalls to protect farmland in the surrounding areas. Since they're president to compare the fight against surging seas as a battle, so I'm going to use war strategy to describe the coastline management. Are we going to defend the front line as the soldiers here, or are we going to fight like the Union soldiers during the Battle of Gettysburg by occupying the high ground on the hills? Hopefully, by the end of this talk, I will be able to convince you that the good physics and economic reason to consider relocation to high ground as an adaptation strategy to sea level rise and storm surge in a warming climate. Here are some of the backgrounds motivating our studies. The left top diagram shows the global mean sea level change over the past century. As you can see that the sea level rose about 20 centimeters over there from 1900 to 2015. You may also notice that over the last 20 or 30 years, from 1993 to 2015, the sea level rose at about 3.2 millimeters per year, much faster than the 0.6 millimeters per year in the earliest 20th century. So the sea level rise rate is accelerating because of the accelerating global warming. On the bottom right here is the global average temperature over even longer period from 1850 to 2019. Over the first 50 or 60 years, from 1850 to 1920, the global mean temperature didn't really increase a lot. But from 1920 to current, the global mean temperature increased by over 1 degree. And you also notice that the warming rate is also accelerating in more recent decades. What does that say to translate into sea level in Chesapeake Bay? Here we look at the long-term sea level record in Chesapeake Bay at 10 tidal stations from south, the Hampton Road near Norfolk, Virginia, to the up north, the Baltimore, Maryland. And as you can see, all the sea level record shows a long-term upward trend. The average, the sea level rise rates range between 3 to 5 millimeters per year, which is roughly double the global mean rise rate. So because the increase in mean sea level, your next high tide is going to be a little bit higher than your last high tide. So that you see nuisance flooding or high tide flooding during sunny days. Here's a picture of Donna Annapolis on April 30, 2014. Here's a picture of the Inner Harbor, Baltimore. Here are some pictures of tidal flooding on the eastern shore of Maryland. I drive on this road to take my son to school. Sometimes I have to look at tidal table, to avoid those places. So in addition to sea level rise, the increase in mean sea level, the tidal range, the difference between high tide and low tide also changes in many places around the world. Here's a look at the long-term time record of tides on tidal gauge station on the US East Coast. You will see that a lot of places have this 9-year cycle, which is a nodal cycle. But you also see some long-term trend. If you look at Washington, D.C. and Norfolk, you will see there's a long-term decreasing trend, about 8 to 9%. If you look at this Philadelphia, Albany, New York, or Wilmington, North Carolina, there's some dramatic increases of tidal range in the early 20th century. As you know, the tides we see in estuary or bay coming from open ocean, how does that tidal wave propagate and change their amplitude depends on the bathymetry and the coastline. A lot of these rapid changes are believed to be caused by channel deepening, channel dredging, because to accommodate larger and larger container ships which come into the port. So over this past century, the sea level rise is probably smaller than some of the big channel dredging work, which can be several meters. But looking in the future, sea level rise is going to make the estuary deeper, but also changes the coastline, how they're going to affect the tidal range. In addition to high tide flooding, hurricanes and tropical storm can also cause flooding. I look at the satellite images on Saturday this weekend. Right now, there are 2 tropical storms in the North Atlantic, 1 hurricane. There are 2 other disturbances. This zombie Paula now just in the news saying is also look like or turn into another tropical storm. In fact, we have had so many storms this year that we run out of names. We're starting to use Greek letter beta to call those names, those storms. One of the notable storms in recent years is Hurricane Harvey in 2017, which hit the Houston area very hard. There's 3 notable effects about this storm. One is the storm accelerates from a category 1 to category 3 when it approaches the shore. Another is the very slow propagation speed. So the storm hangs around for 3 or 4 days in the area. Lastly, which has the most dramatic effect, is the precipitation. Over the passage of the storm, it dumped about over 60 inches of rain. In some places in the Houston area, it dumped about 40 inches of rain in 48 hours. So this increase in rainfall and slow forward propagation speed are 2 factors believed to be associated with climate change. How does it, here is another storm that's closer to home, Maryland, Hurricane Sandy, which hit New Jersey, New York area hard in 2012. It created direct flooding damage about $19 billion in New York City alone, another $33 billion in restoration for the New York State. It also hit the eastern shore of Maryland, the Queensville, Maryland, flooded about 600 homes as shown here. And so what are there any change in trend on the hurricanes? Here is a recent synthesis from World Meteorological Organization, IPCC, that paper published last year. So here's look at number of hurricanes in the North Atlantic region. You will see that this is total number of storms, the green line here. It looked like increase, but it believes that in early days it was underreported. So the adjusted storm do not show a long-term increasing trend in the number of hurricanes in the North Atlantic. If you look at the number of hurricanes hitting mid landfall in the United States, it has certainly a lot of interannual variation, but it doesn't seem to have a long-term trend. On the other hand, if you look at the power dissipation index, which is describe a combined effect, the frequency, storm frequency, duration, intensity, it definitely increases from 1980s. So here are the consensus from that synthesis analysis. So there's definitely a detectable increase in the global hurricane intensity since 1980s, and that can be attributed to global warming. In particular, the number of category 4 or 5 storms has increased in recent decades. Another thing is that we're going to see more extreme precipitation events. We're going to see more Hurricane Harvey-like storm in the future. We are seeing more Hurricane Harvey-like storm with very strong precipitation. What does that translate into sea level extremes? So Marcos et al. Look at a long-term sea level record in 700 tidal stations around the world, mostly in Northern Europe, Europe and North America, but also some in Africa and Australia. They did not mention any long-term trend. What they see is that in some decades, in some places, that it's higher sea level extreme. In other places, they're lower sea level extremes, which seem to correlate with decadal climate variability. You probably cannot see the name of the tidal station here, but they are arranged geographically. So there's also some coherence among the stations. So these two, some geographic coherence and also some decadal variation in sea level extreme have happened in the last few decades. Looking into the future, this is look at the climate model projection on storms. Again, there's this new synthesis released in March of this year from WMO and IPCC. So if you look at global, the number of tropical storms, the frequency actually decreases. This is in agreement. This is because that the upper wind share in upper atmosphere is projected to decrease in a warming climate. So let's make it harder to form storms in the tropical ocean. So that there's actually a decrease. But it's another story about a category 4 to 5 storm. It seems to imply an increase in that category stronger storm. What is very clear is that the intensive storm, the average intensive storm, is going to increase by about 5%. And the rain rate is going to increase by about 15%. If you look at the North Atlantic here, definitely we're going to see more category 4 or 5 major storms. Same story for the increased intensity and rain rate. So how are we going to respond to this sea level rise, high tides, and storm surge? Are we going to use engineered structure like seawalls, levees, or we're going to make use of soft shoreline, a nature-based system like salt mines, seagrass, or oyster reef? Or should we consider relocation as an adaptation strategy? So I will try to address these questions using based on 2 modeling studies. First, look at how does tides respond to sea level rise and coastline management. Second, look at how storm surge respond to sea level rise and coastline management. Here, we look at how the sea level rise and coastline management affect tides in Chesapeake and Delaware Bay. Here is look at the bathymetry of Chesapeake Bay and Delaware Bay. As you can see that most of low-lying areas surrounding Chesapeake Bay are on the eastern shore of Maryland, those rural areas. Dorchester County and counties further south. In Delaware Bay, the lowest lying areas are on the fringes of the lower mid part of the Delaware Bay. So we had developed a model using a structure grid FVCOM model that with high resolution inside those S2 estuaries, but also cover a big part of the Mid-Atlantic Bight, so we can look at the tides coming in. And we consider very idealized two coastline scenarios. One is we allow the low-lying area to be flooded, soft shoreline, so everywhere, there's no seawall, so everything allowed to be flooded. Another is that we put hypostatic seawalls at the current coastline, so we don't allow the water to flood any land. And then we run a model. We raise the sea level, mean sea level due to sea level rise to see what happens. So here is the result for 1 meter sea level rise. Here is the tidal lines and in Chesapeake Bay under the present day. So you have the highest tide about 1 meter at the mouth of the bay and decrease rapidly as tidal energy get dissipated. Reach to a low about 0.3 to 4 meters in the mid bay, then ramp up again in upper part of the bay to a 0.7 to 0.8 meters due to coastline conversion, but also the fact that some of the waves get refracted, superimposed on the incoming waves. So this is what happened when we have a soft shoreline, 1 meter sea level rise. You'll notice that the tidal range in the lower bay increased a little bit by about 2 centimeters. But in most of the mid bay and upper bay, it actually decreased by up to 8 centimeters. On the other hand, if you put seawalls everywhere under the current coastline, you will see the sea level, the tidal range decrease a little bit in the lower bay, but increase by up to 8 centimeters in the mid and upper bay. So the coastline really make a difference, coastline management. And similar story in Delaware Bay. This is the present day tides in Delaware Bay. So you have a tidal range about 1.2 meter at the mouth, increase to about 2 in Philadelphia at the upper of the Delaware River. You also notice that the tidal range on the New Jersey side is higher because of the Earth's rotation effect. So if you have 1 meter sea level rise, if you allow the low-lying area to be flooded, you actually see that the tidal range everywhere decrease everywhere in Delaware Bay. On the other hand, if you put seawalls everywhere, the tidal range increase everywhere in Delaware Bay. So again, the coastline management matters. So here we look at a bunch of runs with sea level rise from 0.5 meter, 75 meter to 1 meter. And again, the dashed line are soft shoreline scenarios, and the solid line are hard shoreline scenarios. So this is a look at the change in mean tidal range. So you can see that if you have hard shoreline, it could increase by about 10 centimeters. If you have a soft shoreline, can decrease by about 5 centimeters. This is look at a line through the center of the bay, the changes on that along channel transect. If you look at the Delaware Bay, you'll see that again, this is a change in mean tidal range. It did reduce up to about a reduction of tidal range up to about 15 to 20 centimeters, an increase of 20 to 25 centimeters where you have a hard shoreline. Sometimes it's good to look at how does this change in tidal range compare to sea level rise, the delta H is the sea level rise. About 50% reduction, soft shoreline in Chesapeake Bay, 10% in hard shoreline in Chesapeake Bay. Much larger changes in Delaware Bay, up to minus 20% in the soft shoreline in the upper part of the Delaware Bay, but plus 10-20% in hard shoreline. So those changes have been found in other places, other coastal ocean estuaries around the world. So this ratio about 10 to 20%. So those are really, if you want to look at tidal flood, peak tidal flooding, this you cannot just look at the changes in mean sea level, that edge, but also you should look at these changes in mean tidal range, because it's the sum of them that determine the peak tidal flooding. So why is that there's such a big difference between soft shoreline and the hard shoreline in terms of tidal response? Here we look at the energy dissipation of tidal energy dissipation. So a lot of tidal, in Chesapeake Bay, a lot of tidal energy get dissipated in lower bay because it runs into the shallow water. Friction take out a lot of energy. Once it's go to the deeper mid bay, there's a weaker dissipation. And if you have a sea level rise and soft shoreline, you have the introduced new shallow area, which cause a lot of frictional dissipation. So basically, when you have a lot of low lying to flooded, you introduce area to dissipate that tidal wave energy. On the other hand, if you have hard shoreline, so seawalls under the current coastline, you force the tide to go further upstream. And then, of course, because it generates stronger currents, you have a higher dissipation in the center channel. Looking at the Delaware Bay, this is the present day. You have a lot of tidal dissipation in the center channel. And when you have a soft shoreline and sea level rise, you bring in those fringe areas, those shallow areas that get flooded, dissipating tidal wave energy. And so that less tidal waves being sent upstream. In contrast, when you have sea level rise and hard shoreline, you actually dissipate a little bit less energy in the lower bay because of deeper water. And you end up sending more higher tides, tidal wave further upstream, increasing tidal dissipation there. So there's another angle to look at those changes. Is look at the phase lag between the tidal current and the tidal height. If the phase lag is 0, that means it's a progressive wave. So the tidal energy gets properly upstream. If it is 90 degrees like here, then it's a standing wave, so that the tidal wave can grow in amplitude rather than propagating away. So here we look at the phase lag in Chesapeake Bay and Delaware Bay. In Chesapeake Bay, most places it's very low, close to 0, 10 degrees or something like that. So it's mostly a progressive wave until you hit the upper part of the bay, where it becomes a mixture or close to standing wave at the further end. You also notice that the shallow areas on in mid bay, and the wave close to be a standing wave. Here too, there's a lot of refraction from the tidal boundaries, and you can see this wave refraction more clearly in Delaware Bay. In Delaware Bay, under current condition, it's a kind of mixed tide in the center channel, but there's a lot of wave refraction from the side boundary. So the phase lag is almost 90 degrees, so it's close to standing waves. So if you have the sea level rise and soft shoreline, you will see that the phase lag actually decreases, particularly at those shallow fringes. So this means that wave become a little bit more progressive. So the wave can run over those shallow areas and get dissipated at those places. So less wave energy being sent upstream. On the other hand, if you have a hard shoreline scenario, you're going to push the, you have some slight increase in that phase lag, more standing waves, wave able to grow in amplitude. A little bit more complicated story in Chesapeake Bay. If you look at future with hard shoreline scenarios, the phase lag increase somewhat, so it's moving away from a progressive wave, more like standing wave, so amplitude can increase. And over here, there's a general decrease of that phase lag, more progressive. In particular, if you look at those shallow regions next to those low-lying areas, low-lying land, you will see that there's significant reduction in the phase lag. So a lot of waves are able to propagate onto those shallow regions, get dissipated. So both the changes in the phase lag, in the wave characteristic, and the dissipation are telling a story. Those shallow regions, if allowed flooded, they're able to take the energy out from the tidal waves instead of sending them further upstream. So if you look at peak tidal flooding, that's the peak tidal flood, the mean sea level plus the half of the tidal range. And if you look at the difference between hard shoreline and soft shoreline, and compare with that the tidal height now, They are not small differences. If you got Washington, D.C., it could mean 11% difference. Baltimore, 18% difference. And Philadelphia can be up to 20% difference. So that how you manage the coastline would make the peak tidal height different in Philadelphia up about 40 to 50 centimeters. So really, really huge difference if you think about how we're going to protect infrastructure in Philadelphia or Baltimore. So the second topic we try to address and use to address those coastline questions is look at how does Chesapeake Bay respond to storm surge in the future climate when the mean sea level is higher, when the ocean is warmer. We also try to see whether the coastline management are making any differences. So we use the Hurricane Isabel as an example. So which moved across Chesapeake Bay in September of 2003, is create widespread flooding in Washington, D.C., Baltimore, Annapolis, and the eastern shore of Maryland. So to address that question, those questions, we developed a regional atmospheric ocean model. The regional atmospheric model is based on weather research forecast model, the WRF model. We have a triple nested domain. So the biggest domain covers the East Coast, but also a big part of the North Atlantic. And a small domain covers Chesapeake Bay with a very fine resolution, about 1.3 meters, which can give us fine resolution wind field, which we can use to drive the storm surge model. This ocean model is the same as we use in tidal studies. So, so we can use very fine resolution in the estuary, about 200 to 500 meters. And we also have, when we look at inundation in a particular area like Baltimore, we can use a few meter resolution. So we can look at street level flood prediction. So here are the climate change scenarios that we consider by looking at the climate model projections. We consider two climate change scenarios, ICP 4.5, which is a medium emission scenario, and ICP 8.5, which is a high emission scenarios, and look at the projection of the increase in sea surface temperature in the North Atlantic Ocean. So in 2050 and 2100. In 2050, increase about 1.1 degree to 1.5 degree. That's the median projection among all the climate models. There's also minimum maximum we consider also. The rate to sea level rise in Chesapeake Bay range from 0.43 meters to 0.47 meters. Looking further in the future, 2100, the temperature increase is going to be larger, but also there's going to be a bigger difference between the two climate change scenarios. 1.6 degree increase in ICP 4.5, but twice as that much as that in ICP 8.5. The sea level rise would be between 0.85 meters to about over 1 meter. So we put Isabel under this high mean sea level and warm ocean temperature, and to see what kind of storm surge we're going to get in Chesapeake Bay. First, we look at the atmospheric model projection for the storm. So the open white circles are the observed track. The black line are the model predictions for Isabel. So pretty good agreement. Here you look at the minimum sea level pressure. It was about, the Isabel was about 955 millibar. So again, there's a good model data agreement. But if you look at the future, 2050, the minimum sea level pressure is going to drop to about 945 for the ICP 4.5, but 940 for ICP 8.5. If you look at the maximum sustained wind speed, it was about 45 meters per second during Isabel. That's going to increase to 50 to 55 meters in the 2050. Looking further in the future, we're going to see more warming, more intensification of the storm. So look at the minimum sea level pressure is going to drop to 940 to 920 millibar, and the maximum sustained wind is going to be in 55 to 60 meters per second. So it's going to be substantially stronger wind that drives the storm surge in the. And the reason for this increase in the storm intensity is related to the fact that when you have warm ocean, it's going to release a lot of latent heat flux. So this is the latent heat release during Hurricane Isabel. This is the for storm in 2100 under the ICP-5. There's a lot more heat released into the atmosphere, which fueled the storm. In fact, we look at all the runs, model runs, you can see a clear correlation. As sea surface temperature increased, there's more latent heat release, but in the meantime, the minimum sea level pressure decreased, almost a linear relationship, which means the intensification of the storm. What does that translate into the storm tide level at a place in Upper Bay like Baltimore? This is the peak tidal height during Hurricane Isabel was about 2.2 meters. Again, this open circle of the observation at the tidal gauge, and the black line is the model prediction. Again, here we consider two soft shore coastline scenario. One is a soft shoreline, one is a hard shoreline. So you see that in 2050, that peak surge height is going to increase to about 2.5 to 2.7 meters. If you have hard shoreline scenario, it's going to increase further to 3 meters to 3.3 meters, depending on it is RCP 4.5 or 8.5. Looking into further into the end of 21st century, you will see that soft shoreline increased storm height to about 2.7 meters, but came up to about 3.5 meters in hard shoreline scenario. So again, we see clearly that how we manage the coastline is going to make a big difference in terms of the height of storm surge we're getting. So this is just not the difference. It's just not found only in Baltimore. You see everywhere. Here we look at the a number of stations in Chesapeake Bay, from Norfolk, Virginia, to Annapolis, Cambridge, Louisiana, and a number of places. The gray line are the surge height in 2003, and the green is ICP 4.5, and we have the arrow bar here representing the range of climate model projections. Red are the ICP 8.5. So of course, there's no difference in Norfolk between hard shoreline because they're just at end. But when you go towards Upper Bay, like Annapolis, you see the difference here. Start to show very big difference. Even in the mid bay, like Cambridge, where Humboldt is located, there's rather big difference. Just a little bit south and north of that flooded area, you start to see that difference in the peak surge height. And so we were wondering what contributed this storm surge height increase. Is that due to sea level rise, or is that due to warming, SAT increase? So we did a couple more rounds, 2 more rounds. And the dashed line here is the storm surge during Isabel. So if you just increase the sea level rise, you only increase the mean sea level. It does not, it's almost the same as in terms of surge level, it doesn't really affect. So this is actually different from the tides. Tides will show you that the sea level rise affected. This is because the storm surge occurs at a lower frequency. It's almost like a bathtub effect. However, when you increase the warming, it has a big difference. So the warming, in fact, contribute to most of that increases. Again, there's a big difference between soft shoreline and high shoreline, and particularly not in Norfolk area, but in Cambridge, in Baltimore, in the mid bay and upper part of the estuary. So to get a little bit further insight into these differences, we look at the energy budget of the storm surge. So this is look at the change of the kinetic energy. In fact, that this actually can be converted into change of potential energy. So you can move to the other side. So this will be the net change, time rate of change of total energy of the storm surge. So what are the contributing factors? One is the wind energy input. That's the wind energy applied to the water in the Chesapeake Bay. This is the one. This is the dissipation. Another one is the incoming flux. So this is the storms coming from the ocean into the bay. Here, we want to, we set the control volume right at the current coastline. So on a current coastline. So if the water if the storms will flood the low-lying land, it will consider be captured by this lateral flux. Oh, sorry. Before I go to the next slide, if you look at the prime balance of this energy budget, it's a balance between wind energy input and dissipation. So these are two biggest terms, but they always oppose each other. Another thing you notice is that this yellow line here, which is representing the incoming and tidal flux. So that's smaller than the wind energy input, but significant. What's more interesting is look at the next order balance in this energy budget. So what we did was to look at the net difference between wind energy input minus dissipation, as shown in the green line here. And the yellow line is the incoming tidal storm surge energy flux. And the blue line is the change of the storm surge energy inside the estuary. As you can see, that what's driving that increase is mostly due to this incoming storm surge energy. That difference between the wind energy, local wind energy input minus dissipation is actually pretty small. After that, the input runs out, the dissipation is taking out is driving that slowing down of the storm surge current. And if you look at the hard shorelines, you also notice there's this little red curve here, and this is Hurricane Isabel in 2003. So there's a little bit of a negative value here, much smaller than the other two. This because that during Isabel, some of the low-lying area got flooded. So some of the energy leak out of the side boundary of the current coastline. Once the water retreat, so you have a little tick up increase. This is because the water retreating back to the bay, putting some energy back into the bay. So this, nevertheless, it's a small term here. So on the current condition, and if you compare with future 2100 with sea level rise and warming in a harsh shoreline scenario, of course, because you build a seawall, nothing can leak out of side boundaries. So you still have that balance between incoming energy flux, the change rate of the energy, and the balance between local wind and input and dissipation. Now, if you look at the soft shoreline scenario, you start to see something interesting. You will see that this red curve here, which is leakage of energy through your side boundary, it's bigger. So still, during the storm coming up, you have the energy leaking out. You basically store water away from it. When the storm slowing down, you get a little kickback. And if you look at the time evolution of the change of total storm surge energy, this is the this is the E. How does that energy change over time? You will see that right now that leakage is only a small part, but in the future, with soft shoreline, you can really take some punch out of that storm wave energy. This is the sort of energy underpinning of that difference. So we want to look at the impact of this more intense storm and sea level rise on inundation. Here, of course, we don't put any seawalls here. You will see that this is how much land was flooded over Chesapeake during Isabel, mostly on the eastern shore, on lower eastern shore, because it's lowest place. If you look into the future, like 2100 for the two climate change, there's more places will be flooded, but also you notice that many places on the western shore will be flooded even on this bay wide scale. If you can sum up the areas that might be affected, it's about 1,900 kilometers square, about 10% of the surface area were flooded. By the 2100, it will be 3,300 kilometers square, 60% increase. And you can look at the eastern shore, Dutchess County more closely. This is what flooded during Isabel. This is what projected to be flooded during 2100 with high emission scenario. So interestingly, the area that will be flooded does not expand so much because there's a pretty steep topography over here. So very low here, then slopes start to rise. But the water depth definitely increase a lot. looking at an urban area like Baltimore, this is what the model projected flooding during Isabel. So some of the couple streets around the inner harbor area were flooded, as reported in anecdotal reports. Also, the Little Italy area were flooded. This is what the model projected flooding in 2050 and 2100. So you see, there's more area to flooded. You can do some calculations. You find that inland area was about 2 kilometers square in Baltimore in 2003, will increase to 6 kilometers square 3 times in 2050, 9 to 10 in kilometers square in 2100. And if you look at the average depths, will also increase. It's a little bit interesting that it decreased a little bit because as you increase the inland area, the average depths can decrease. But if you look at 2100, it will definitely be deeper. Also, average inland area is a bit larger. And we took those estimates, look at the square footage of total of the commercial building being flooded by affected by flooding. Use FEMA's depth damage function, which basically says if it is 50 centimeters, it will cost so much for the building and content. If the 1 meter costs more, and then we just look at the integrated effect. And so I'm not an economist, so don't believe absolute numbers here, but just look at the change in the sum. So it's about 3 to 4 times larger in 2050 in terms of the estimated probability cost, but 5 to 6 times in 2100. Since we're still on this number game, so I did some back of the envelope calculation on various coastline management options to protect Chesapeake Bay coastline. So I look at the NIC report in 2014. 1 square miles of flood wall, like seawall, costs $28 million. A levee costs $8 million per mile. Look at, this is very naive and simplistic calculation, just give you some ballpark. So the total length of Chesapeake Bay shoreline is about 12,000 miles. So the estimate cost would be $330 billion for seawalls, $98 billion for levees. Even we look at this lower county, Dutchess County, where the Humboldt Lake is located, the length shoreline is about 15 miles. The estimate cost would be $42 billion for seawalls and $30 billion for levees. So this would be astronomical numbers for Laurel County. What about using nature-based system? Again, I look at that NIC report. So wetland restoration costs about $40 million a mile. Seagrass restoration costs about $30 million a mile. If you want to do oil reef restoration, that's going to cost $25 million a mile. That is translated to about comparable cost as engineered structure or lower, but there are co-benefits to ecosystem, I understand, and that need to quantify. A third option might be, why don't we just put a storm barrier at the mouth of Chesapeake Bay, like what people are doing here? And I look at the construction New Bedford Hurricane Barrier in 1966, about 0.85 mile long, cost about $140 million in current dollar. So I added up. So length of Chesapeake Bay Bridge Tunnel is about 24 miles. So that will cost about $3.4 billion, which is much smaller than what the previous two estimate. But there are known side effects. If you restrict exchange at the mouth of Chesapeake Bay, what's it going to do to coast habitat, saltwater intrusion? There's a study by Du et al. In 2017 suggests that the tidal range is going to be smaller, the stratification is going to be stronger, and racing time is longer. This is going to have implications in terms of hypoxia, water quality, harmful algal blooms. That's further study will be needed to look at the impact of constructing such a storm barrier. So here comes the last option. Look at relocation as an adaptation strategy. I know it's not just a money issue. People have heritage, culture, their livelihood attached to a certain area. It's a very difficult decision to decide to move a community or even a small community to a remote to another location. But this option is being considered. For example, that in Isle de Charles, in the barrels of the southern Louisiana, there's this part of land, rich land, that in 1950 used to have 300 houses, and but today had lost 98% of the land due to erosion, sea level rise, and so in fact that now there's only 100 people left on that community, and in fact they got federal funding a few years ago now to relocate to this another higher ground, and so we should, this is something that when we have faced a long convoluted coastline with no line areas, this is another approach we should consider. So to summarize, even though sea level rise and intensified storms in a changing climate is a global phenomenon, but sea level we see in a bay actually depends how we manage a coastline. This is something that I didn't realize when I started to work on those projects, but it's come pretty clear. This gives a specific result on the changes of tidal range and storm surge because of the coastline management. And the physics behind it is that the energy dissipation over those shallow flooded area weaken the upstream propagation of the tidal wave and storm surge. So that if you allow those waves to to be dissipated, less gets sent to upstream locations. Another thing is that we should really think what the military leader might think, that sometimes fight from high ground might be a good strategy. Thank you.
That's great. Thank you very much, Ming. Yeah, we have a couple of questions. And if you have any questions, please submit them by chat, and then we could try to unmute people. So this is a question from Kevin Wagner. Regarding the IPCC projections, what would you say to county and municipal elected officials who do not agree with the numbers or the science behind them? Some flat out refuse to adopt local hazard mitigation plans that include this information.
That's a very good question, and this goes beyond science, I guess. And we just have to communicate. When they make their projections, they did consider the range. They did. First of all, if you look at all the climate model, they have to make a prediction over the past 100 years or something like that, which agrees with observation. So there's validation. Before you can have any confidence of projections, we have to do some what we call hindcast, to look back in time and to see whether your model can reproduce the past changes. So I don't have a figure here, but those climate models, most of them do a very good job in predicting past changes in warming, in sea level rise. So that gives you some confidence that those models are a good representation of the nature. Okay, looking into the future, yes, there's uncertainties. We don't know exactly how the emission scenarios, how much carbon dioxide is going to be released into the atmosphere, and there's also that's why we consider different climate change scenarios, like different IC representative concentration pathways. There are also different models produce different model results. So we not only give a projection, but it gives a certainty range, so that and then we need to communicate that a certainty to the public.
Mm-hmm. Well, this is a related question, Ming. Roger Wang asked, "What are the major uncertainties in this current study?"
What we do, of course, there's climate change uncertainties in climate model projections. we use to drive our model. We use sea level rise, global sea level rise projection, and we use the warming projections. Those have uncertainty, which we did consider in our model runs, but also in terms of it's a numerical model, and so that as you see, before we make any future projection, either for tide or storm surge, we want to do, we want to validate it. So, and you see that there's pretty good validation, but it's not the errors. I mean, it's not 100% agreement for sure. And we need to, do more studies for sure. We only consider one storm, which is Isabel, as an example. Maybe we should consider other storms to see what kind of result we'll get.
Thanks. Here's another question, Ming. How do you estimate baseline conditions for the impacts of hardened edges or soft edges on tidal height? Because the current observations are clearly a mixture of both, and some areas of the bay are naturally hardened, i.e. Calvert Cliffs.
Yeah, no, this is another thing. We did something, I acknowledged in the beginning that we did something very simple. Either allow all lying area to be flooded or put a seawall. Of course, right now, about 25% of the Chesapeake Bay shoreline are hardened somewhat. But mostly, I think for rip wraps, they're for shoreline stabilization rather than for flood protection. So they're usually very low. So they can dissipate some waves. But in terms of storm surge, they're probably not going to make difference. But I agree, this is one of the areas that we need to improve in the future modeling, is to have a more realistic representation of coastlines. Consider those hardened structures somewhat. They're going to have a little bit different impact on how they dissipate waves, but probably minor effect on storm surge.
Yeah, thanks. Here's another question. How important is the timing of an incoming storm with the timing of tide, and how the storm surge versus tidal range stories plays out with future sea level rise?
That's absolutely right. If you have a very high storm surge, but it happens to be low tide when it arrives, then the impact will be low. We have examples of that. And if on the other hand, the storm surge comes when you have a high tide, so you get boom, I think you have a trouble. Yeah. So that's the phasing between tides and the storm surge is critical. But when you plan for the future, you don't count on that luck, that phase difference. You always prepare for the worst.
Yeah, boy, some great questions coming in. Whether speaking of hardscape or natural shorelines, will we have to settle on a single solution throughout the bay or a suite of solutions? What of inappropriate solutions in the past from a free market approach to shoreline management?
Of course, a suite of solutions. There's no one, one solution fits all the bills. They are so. For example, the urban area in Baltimore, of course, let's make, Washington, D.C., there are major infrastructure you have to protect, whether using, engineering structure or whatever else, nature based or accommodation both. So you have to protect. But if there's some areas that, not a lot of population and things like that, then maybe we should consider other strategies. So it's not going to be one solution. We should try all different approach in different areas. Another point. Okay,
go ahead.
Maybe before while I'm still on this, I think that another thing that I think we need to think about is the community on Chesapeake Bay, which means from Virginia, from DC and Maryland. We all need to talk because the water are connected. And so as you can see that what's happening on low-lying essential area is going to make a difference in terms of Washington, D.C. and Baltimore. So also the different communities, urban, rural area has to talk to each other when to come up with a collective solution. Because if you only think that let me put a ball head around my house, but you end up sending the waves, cause erosion next door to your neighbors. So another thing is that we, when we come up with solution, everyone has to talk to each other, try to, have a way that the best to everybody.
Are rainfall volumes from these storms also included in the inundation models for urban areas like Baltimore? Seawalls usually come with rainwater pumps, which may not be able to keep up during a tropical cyclone.
Yeah, no, we did not consider in our model. We did not. The WRF model does produce rainfall, but in our ocean model, we did not consider rain rate. The precipitation on flooding. But that's something you need to include some hydrology, the model into that. You also consider that. So something that I'm looking forward to work with hydrologists or atmospheric scientists considering additional land precipitation. Yeah.
All right, here's another question. Are there local subsidence issues in Maryland coastline? Did you consider it in your sea level rise scenarios?
Yeah, we did. And so the sea level rise rate is actually uneven. Not only that, the Chesapeake Bay is twice as much as the global average. It's also uneven in different places. Like Norfolk area, it's sink faster than Washington, Baltimore. So we, in this modeling study, we use a uniform, because it's just only a uniform average subsidence rate, and we did not consider the regional differences. The reason is that the difference is probably about 10 centimeters, but the future projection of CRY by the end of 20 is 1 meter. So it's a relatively small difference. In order to consider that regional difference in subsidence rate, we have to do quite a bit more work into the modeling and try to change the bathymetry differently.
So Ming, this is a question, being down here in Dorchester County as we speak, quite close to us is Blackwater National Wildlife Refuge that, is worked with the Nature Conservancy and other NGOs to expand the marsh area. There are marsh restoration programs in Delaware. Is this a strategy, even the state of Maryland through open space, buying up land to create more marshes that could be used to dissipate the water? Could you run these kind of scenarios in your model?
Absolutely, yeah. So again, there's another simplification in my model. We didn't really, we did consider the friction created by land surfaces, but apparently different vegetation can cause a different rate of wave energy dissipation. And so yeah, so that those, if you buy up those land, allow those land area as a place to dissipate or dissipate tidal wave energy or storm wave energy, that's going to help mediate some the problem further upstream. And yeah, that's certainly a very good strategy.
Yeah, sure. I would think people in Baltimore would want to chip in. All this water is getting flooded up to the top of the bay. So one last question from Amy Nelson. Nature-based solutions often bring additional services benefits beyond shoreline protection. Do you know of any good studies of the economics of soft solutions versus hard?
We can talk offline. There are a lot of papers and things like that on that. And I would also mention that if you're interested in, you can participate. Web panels that series we're organizing in October and November, when we're probably going to mention those co-benefits. Yeah.